Welcome back to Numerical Analysis, everyone. Today is Wednesday, April 1st, and we're going to be talking about Euler's method today. Euler's method, you might guess, was named after Leonhard Euler, who was certainly one of the great mathematicians of all time. I highly encourage you to read his Wikipedia page. It's fascinating. He was a prolific and profound mathematician. And if you do read that page, you'll see a lot of interesting information. For instance, one little thing, the reason we call the base of the natural exponential system E is because of Euler. And there's a lot of other good reasons to hold Euler in high esteem. In particular, he had something very useful to say about the problems we've been considering of late in our class, namely differential equations. His method, Euler's method, um, really has to do with a numerical technique for finding solutions of equations that can help us in situations where our power series method didn't work. And so the way I'd like to introduce Euler's method is actually by looking at a problem from the point of view that we've been taking up to now, that is trying to do a power series solution for this equation, this initial value problem. dx dt is minus x squared plus t, and x of 0 is equal to 1. If we start along the lines that we've been working with, we try to extract derivative information. Of course, the 0th derivative is already given to us, and we can pretty easily get information about the first derivative just by using the differential equation. So we do that as we've done before, and we find that the first derivative at time t equals 0 is negative 1. The problem starts in this case when we start looking at second and higher derivatives. If you look at the second derivative here, we can proceed as we have. That is, the second derivative is the derivative of the first derivative. The first derivative is given by minus x squared plus t. Take the derivative there, remembering x is a function of t, so the derivative of minus x squared is minus 2x dx dt, plus the derivative of t, which is just 1. And then dx dt we get from the equation again. So we get this expression, and I've just multiplied it out here to get the second derivative as 2x cubed minus 2x times t plus 1. That's already a little more complicated than we've seen before. And if you try to go for higher order derivatives, like the third derivative or the fourth derivative, the complications only build up. And that's essentially coming from this part, this aspect of the problem right here. Dx dt is negative x squared plus t. That negative x squared makes our problem nonlinear in the variable x. And that's going to cause a lot of this complications that we've seen to just, build up as you take higher and higher derivatives. So it's not that you can't take higher and higher derivatives. It's just that they get more complicated as we go on because of this nonlinearity. And so there's really no obvious overall pattern you can see beginning to develop here. And the situation doesn't get any clearer if you look at the fifth derivative and sixth and so on. So if there's no obvious pattern going on, then the power series solutions that we've been using up to now aren't going to be feasible, because they all depended on us seeing this pattern as you start taking derivatives. So what can we do in place of that? Well, we do have some derivative information. And let me just kind of stick to the most basic information. The derivative information we can pull straight from the initial value problem itself, which of course is that the 0th derivative is 1 when t equals 0. And we saw previously that when t equals 0, the first derivative is negative 1. So just using that alone, we can form a Taylor polynomial for the solution centered at t equals 0. It would have to be just the first degree Taylor polynomial. So that would be x of 0 plus x prime of 0 times t. And using what we know, we see that this is that first degree Taylor polynomial for our solution centered at t equals 0. Now, the idea here is going to be that that first degree Taylor polynomial is actually a good approximation of the solution as long as t doesn't wander too far from t equals 0. And so Euler's idea was, well, take a small step away from t equals 0 and let the Taylor polynomial give you the approximate solution at that one step away, and that's what we're gonna do here. So Euler's idea was, the Taylor polynomial is close to the exact solution for t close to 0. So choose a small step away from t equals 0 and compute an approximate solution using the Taylor polynomial. And so you would have now a value x1 corresponding with time t1 that you could actually compute. And then to go from there, you would simply repeat that same process just for a slightly different problem. Our solution x has to satisfy the same differential equation, but now we have information that at time t1 we have an approximate solution whose value is x1. So we can just repeat that process from that point onward. So let's try this using a step size of delta t equals 0.1. By the step size, I just mean the sort of step we're going to take between the current t value and the next one. So to get started, we would our current t value at the very first step would just be the t value in the initial condition. So that's going to be t equals 0. I'm calling that t0 equals 0 to emphasize that that's our very first value of t, our initial value of t from the initial value problem we're going to call t0. The next t value we'll call t1, and that's just the previous t value plus our step size, so it's going to be 0.1 here. And then our approximate solution we'd get just by plugging that next t value into the Taylor polynomial that we saw previously. So that we're going to call that x1. That's our solution value at t1. And remember our Taylor polynomial was just trying to find it here, 1 minus t. So we get p1 of t1 would be 1 minus t1, 1 minus 0.1 or 0.9. So now we have a new tx pair corresponding to an approximate solution. When t equals 0.1, we find x1, the approximate value of x is 0.9. Let's move on to step 2 then. Step 2 is going to correspond to basically starting at this point and computing another step away for that differential equation. So our current value now for step 2 is our t1 value from step 1, 0.1. We look at our derivative information. What is the derivative of our solution at time t1? We want the 0th and the first derivatives at time t1. So the 0th derivative would just be x at t1, but when t1 is 0.1, the x value we have is our x1 value, which we had previously calculated to be 0.9. And then the derivative, x prime at t1, would come again from our differential equation, be minus x1 squared plus t1. So we get minus 0.9 squared plus 0.1, which turns out to be minus 0.71. So this is our 0th and first derivative of our solution evaluated at time t1 now, which is 0.1. We can use those to form a Taylor polynomial of degree 1 centered at our current time, which is t1 equal 0.1. So here's the generic formula for a first degree Taylor polynomial centered at t1. And I'm just plugging in what I know. X of t1, which is x1, which is 0.9. X prime of t1, which is, we know, is 0.71. And of course, t1 is 0.1. So our first degree Taylor polynomial now centered at time t equal 0.1 would be 0.9 minus 0.71 times the quantity t minus 0.1. So what I'm going to do to compute my next solution step is simply plug in my next t value, which would be my t1 plus my delta t, which you remember is 0.1. So that's going to be, I'm going to plug in t equal 0.2 to this thing. And that's what you see happening here. X2 is our polynomial evaluated at the next t value, which is 0.2. So I'll plug that in here, and you just do the arithmetic, and you get 0.829. So our second computed solution point is T2x2 is 0.829. And if you take a look at the results so far, I've just tallied what we've done so far in this little table here. We started out with a t value of t0 equals 0. Corresponding x value was 1. t1 was 0.1. And the corresponding x value we found was 0.9. And now in the second step, we found our t2 was 0.2, and the corresponding x value was 0.829. And you see I've just plotted those kind of by hand here real quickly in this little chart here, and you can see a solution beginning to develop. And the essence of Euler's method is just to sort of continue this process for as long as you'd like, and you develop more and more points along the solution curve. So let's take it one more step. Step 3, the current value is the one we had from our previous step. T2 is 0.2. Extract the derivative information. The zeroth derivative at time t2 is just our solution value that we found previously. That's 0.829. The first derivative at time t2, you're going to be using the differential equation along with the value you already have for time t2. So it's minus x2 squared plus t2, that's coming from our differential equation, and then use the values we already have for x2 and t2, and that's what I'm doing here. Do the arithmetic and you get minus 0.4872. So those are our zeroth and first derivatives evaluated at time t2. You can use those to form the Taylor polynomial for the solution at time t2 now. So it would be, here's just the generic formula again, the function at t2 plus the derivative at t2 times t minus t2. And now I'm plugging in what I know for each of those. So we found that x2 was 0.829. We found x prime of t2 was minus 0.4872 times t minus t2. That, again, t2 is 0.2 here. And what I do to get my solution for the third step is plug in, I take one step forward from t2. That is, I'm going to have t2 0.2 plus my step size, which you remember is 0.1. So I'm going to plug in 0.3 here to p1 to get my next solution value. You see that happening over here. T2 plus delta t, so that's our 0.2 plus 0.1, so that's our 0.3. That's the time at the next step. And plug that into our first degree polynomial, and you get this, and then that turns out to be 0.78028. And I've again tallied my results over here, and you can see them there. You see another point along our solution trajectory developing there. And so that is the essence of Euler's method. If you connect those solution points by by just a smooth curve, you begin to see some idea of what the solution might look like. And so get this slide up here where y'all can see it. It begins to look like a decreasing, at least from 0 to 0.3, concave up, perhaps, function. It would be our solution curve. So the essence of Euler's method is to just keep doing this until you get the solution sketched out, or at least an approximate solution sketched out for the time interval you're interested in. I've gone ahead, obviously this is something you'd want to program a computer to do. I've used MATLAB to compute Euler's method for this very problem. For values of t between 0 and 1, and I'm using that same step size, of 0.1 here. And so the blue curve is the solution curve generated by Euler's method. I've also plotted the exact curve, which I obtained by other methods, other numerical methods, in red here. So you do see that Euler's method is giving you only an approximation of the solution, and actually the error is pretty significant here. It's on the order of 0.05 or 0.03 or something. So Euler's method is not giving you an exact solution, but you can see that it's giving you an approximate solution. And I bet if you thought about it, you could guess how you might make that solution a little more accurate, right? Decrease the step size. Well, if you do that, I won't go through the calculations by hand again. Let me just show you the result. Instead of using a step size of 0.1, I'm going to use a step size of half that, 0.05. And here you see the Euler's solution in blue is now more closely approximating the exact solution in red. And by decreasing the step size even further, you could get a more accurate solution. There's a trade-off there, though. Obviously, if I decrease the step size, I have to compute more points along the solution to get a full picture of what's going on between times 0 and 1. In fact, having the step size would double the number of solution points you need to compute. So that is a trade-off we have to be aware of. And another aspect of it is, how would I know what the error in the solution is if I don't have access to some magic that gives me the exact solution to compare it to? So we'll have to address those topics going forward. But this is the basics of Euler's method. And your next homework, which is homework 21, will just ask you to go through a few steps of the method for another problem. So let's summarize what we've done so far for Euler's method. So here's how Euler's method would work for a general first order initial value problem. So notice I have dx dt is just some function of t and x now, and an initial condition x of t0 equals x0. So how would Euler's method work? Well, it's going to give you output that's ordered pairs of t comma x values for as many steps as you want to do, and these are going to be approximating the values on the solution curve. You will have a parameter. There is a parameter, in other words, sort of a user-defined input to the method, and that's the step size. So that's delta t. That'll be given in your homework problem. And then you start doing the method. So step 0 is to get your initial t0, x0 pair from the initial value problem. And so that's just what you're going to be reading off from the initial condition. And then once you have the t comma x pair from a given step, you're ready to go to the next step. And so I'm calling that just step n plus 1. But remember, you'll have in hand the t and the x value you got from the previous step in order to generate your next t and x values. So how do you do that? Well, the first thing you do is you compute the derivative information you need for that first degree Taylor polynomial, and that's the 0th derivative evaluated at t sub n. And remember, tn is going to be coming from your previous step. Well, that's just x of tn, and that's given by xn, the xn value from your previous step. So that's the 0th derivative. The first derivative, you're going to be just x prime of tn. You have to use the differential equation part of it. X prime of tn would be f evaluated when t is tn and when x is x of tn, or just xn. So x prime is going to be f of tn and xn. Then your Taylor polynomial you can put together, and this is of degree 1 here. is and centered at Tn is x of Tn plus x prime of Tn times the quantity T minus Tn. And then just use what you know about x prime of Tn from up here. And so this will be your first degree Taylor polynomial. Notice that xn will be a constant here because it's known from the previous step. And actually this number too will be some constant because it's known from your dE and from the Tn and xn values you got from the previous step. The only variable here really is the T. So this will be this is an equation of a line. This is your first degree Taylor polynomial. Then to get the next approximate solution value, your Tn plus 1 is just your current Tn plus your delta T, and your x of n plus 1 is just the value you get from the Taylor polynomial below, the one we just talked about, this guy. When you plug in t equals t sub n plus 1, this value right here. So I'm just showing you that right there. And that'll give you your next x sub n plus 1 value. And with those two in hand, you're now ready to go to the next step. So you can continue the process for as long as possible. So I'll have a little problem posted for you pretty much simultaneously when this video is posted, and I'll just ask you to go through 3 or 4 steps of that, and then we will pick up from here going forward. Hope you're doing well. Let me know if you have questions as always, and we'll see you soon.